Problem number 8. A block of mass m equal 3 kg is moving on a horizontal surface towards a massless spring with the spring constant K equal 80 Newton per meter. The coefficient of kinetic friction between the block and the surface is mu K equal 0.5. The block has a speed of v equal 2 meters per second when it first comes in contact with the spring. How far will the spring be compressed? Solution. Here we can use work energy theorem. It means that initial energy, which is completely kinetic energy for this mass, turning to potential energy of the spring plus work done by force of friction. Let's write this expression. This is the formula. 1/2 mv squared, that's kinetic energy for mass, mu k mgx, that's work done by force of friction, and 1/2 kx squared, that's final potential energy for compressed spring. As we can see, this is a quadratic equation to x. Let's put the numbers and count the result. This is our equation in numbers, and after simplification we have this equation. Let's try the solution. This is the solution for two roots, but we have to take a positive root, not negative. And for positive we have 0.24 meters, which is answer B. Problem number 9. A uniform spherical planet has a radius r and the acceleration due to gravity at its surface is g. What is the escape velocity of a particle from the planet's surface? Solution. Escape velocity in some particular point means that total energy of this satellite is 0. Let's write this expression for total energy. Right on the surface of this planet we have total energy equal kinetic energy plus potential energy, which is negative g m over r, where r is radius of this planet. Let's express this through g. We can replace this expression for potential energy by this formula, and here g multiplied by mass of planet and divided by r square, that will be acceleration due to gravity on the surface of this planet. So that's equal mgr. And when we put this to this equation, we can find what is the escape velocity. Escape velocity equal square root from 2gr. That's answer C, correct one. Problem number 10. 4 objects are placed at rest at the top of an inclined plane and allowed to roll without slipping to the bottom in the absence of rolling resistance and air resistance. Object A is a solid brass ball of diameter d. Object B is a solid brass ball of diameter 2d. Object C is a hollow brass sphere of diameter d. Object D is a solid aluminum ball of diameter d. Aluminum is less dense than brass. The balls are placed so that their centers of mass all travel the same distance. In each case, the time of motion t is measured. Which of the following statements is correct? Solution. Here we need to take into account what is the expression for moment of inertia for each object. Moment of inertia for any round object we can express in form of I equal beta mr square, where beta could be some kind of coefficient. For a hollow sphere, beta equal 2/3. For solid sphere, that's equal to 2/5. And the result depends only on this beta. If we have beta greater, we have greater time, because for more beta we have more energy going to rotational motion and less energy going to translational motion. It means that linear acceleration for such objects will be less. It means that the result is the same for objects A, B and D, and for object C time will be greater. So that's the answer.